Welcome to Module 11. In this module, we'll explore the concept of the definite integral. Remember how when we introduced derivatives with a limit definition, we did this to demonstrate it as a logical, if somewhat complicated, mathematical process. However, after the concept was developed, we learned shortcut formulas that made the process much simpler. In short, the same is happening in this module. We will develop the concept of the definite integral. However, in the end, we will have easier ways of actually computing them than what is shown here. While you could skip to timestamp 10:15 for the key takeaway needed for future lessons, I encourage you to follow along with the development of the process. There's fascinating mathematics involved, and I think you'll find that it helps you understand where the important formulas come from. So let's get started. I'm going to begin with a couple of mathematical formulas that you may have seen at some point. First, whenever you see a capital sigma, this means that we're adding something. So in the first formula, we have the summation of I, where I goes from 1 to n. That is, we have 1 plus 2 plus 3 plus 4, and all the way up to n. And what this formula says is that this sum is equal to n times n plus 1 over 2. In the second formula, the summation of I squared, which is 1 squared plus 2 squared plus 3 squared, all the way up to n squared, is equal to 2 times n cubed plus 3 times n squared plus n all over 6. So let's just hold on to these formulas for a bit. We're going to shift to thinking about area. Now there are certain geometric figures for which it is easy to find the area, things like squares or rectangles, perhaps triangles or circles. Suppose, however, that we wanted to find the area of a region under the curve of a certain function. For instance, let's say that we wish to find the area under f of x equals x squared, where x goes between 0 and 4. This region is somewhat irregular, which adds to the complexity of finding the area. One approach is to estimate the area. Now we can do this by splitting the range of x values into 4 equal parts, and then construct rectangles whose heights are given by the function values. The estimated area is then the summation of the width of each rectangle times the height of each rectangle. Now the width of each rectangle is 1, and the heights are f of 1, f of 2, f of 3, and f of 4. So our estimate is 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4. Now this equals 1 squared plus 2 squared plus 3 squared plus 4 squared. Now this is easy enough to find, but how about we use our formula? Here, n is equal to 4, so the sum is 2 times 4 cubed plus 3 times 4 squared plus 4 all over 6. And this gives us 30. So our estimated area is 30. However, we can see that this is an overestimate because there are parts of the rectangles that extend above the region we are interested in. Imagine that we increased the number of rectangles that we use. We can see that doing so reduces the overage area. So our plan will be to fit in many rectangles to make the error as small as possible. So suppose that we split the range of x values into n parts. Then, the width of each rectangle would be the range of x values, which is 4 minus 0, or 4, over the number of rectangles, which is n. Let's call the first x value x0, and we can see that this is equal to just 0. The next x value is x1, which is 4 over n units over, so x1 equals 4 over n. The next one is x2, which is equal to 2 times 4 over n. The next one is x3, which is 3 times 4 over n. In general, if x sub I is the x value corresponding to the ith rectangle, then x sub I is equal to I times 4 over n, or we can write that as 4i over n. Now, the height of the ith rectangle is f of x sub I, which is equal to x sub I squared, which is 4i over n quantity squared, or 16i squared over n squared. So, with n rectangles, the estimated area is the summation of the width of each rectangle times the height of each rectangle. which is equal to the summation of 4 over n times 16i squared over n squared. Now I'm going to take everything here that doesn't involve I and bring it out front. So I'll rewrite this as 64 over n cubed times the summation of I squared. And remember, the summation of I squared is equal to 2 times n cubed plus 3 times n squared plus n over 6. So multiplying all of this gives us 64n cubed plus 96n squared plus 32n over the quantity 3n cubed. Remember when we used 4 rectangles? The area here would be approximated by 64 times 4 cubed plus 96 times 4 squared plus 32 times 4 over 3 times 4 cubed, which equals 30 like we saw before. How about we try using 10 rectangles? Here we find the estimate to be 24.64. If we use 1,000 rectangles, the estimate is 21.37. As we use more and more rectangles, as expected, we're reducing the overage area. So it seems logical that the exact area is obtained when the number of rectangles approaches infinity. That is, the exact area of the region is given by the limit as n approaches infinity of 64n cubed plus 96n squared plus 32n over 3n cubed. Now we find that this is equal to 64 over 3, which is 21.33. It seems somewhat remarkable that we can find the exact area of such an irregularly shaped region. Now let's think about this process again. We started with a region that was bounded by a function f of x over some range of x values, let's say a to b. Then we divided the region into n rectangles. We found the area of each rectangle, and then allowed n to approach infinity. Now we might write this process as the limit as n approaches infinity of the summation of the height times the width, which is equal to the limit as n approaches infinity of the summation of f of x sub I times some delta x. However, mathematically, we generally use the notation the integral going from a to b of f of x dx, and this is referred to as the definite integral. So the definite integral of f of x from x equals a to x equals b represents the area under the curve of f of x over the interval from a to b. Looking back at our original problem, we can see that the area that we were seeking is given by the definite integral of x squared from x equals 0 to x equals 4. Now comes the fun part. Say that we start with a function f of t, and we integrate it from some constant a to the variable x. Here, since x is a variable, we can change it. And notice that when we do, it changes the amount of area given by the definite integral. So here is a question. At what rate does the area change as x moves? Now think about that. When we ask about a rate of change, we're talking about a derivative. So the question is, what is the derivative of the definite integral of f of t from a to x? This question is answered in what is called the first fundamental theorem of calculus. The first fundamental theorem of calculus says that the rate at which the area is changing is equal to the height of the function at the value of x. That is, if we take the derivative of the integral going from a to x of f of t, this is just equal to f of x. Now think about that for a moment. When the function is high above the x-axis, the area changes rapidly. But when the function is close to the x-axis, the area doesn't change so quickly. So it makes sense that the rate at which the area is changing is related to the height of the function. So, the first fundamental theorem of calculus tells us that if we take the derivative of the definite integral from a to x of f of t dt, then we get f of x. Now this implies that the integral from a to x of f of t dt is an antiderivative of f of x. So for simplicity, I'm going to call this function capital F of x. So capital F of x, which equals the definite integral from a to x of f of t dt, is an antiderivative of little f of x. Now let's hold on to that thought for a moment. Our ultimate goal is to be able to calculate the definite integral from a to b of f of t dt, since this represents the general area under the curve over an interval. So consider what happens if we perform the operation capital F of b minus capital F of a. This gives us the definite integral from a to b of f of t dt minus the definite integral from a to a of f of t dt. Now looking at this second integral, if we think about the area under the graph of f of t over the interval from a to a, it should be clear that this area is 0. And this brings us to our conclusion. The definite integral of a function f over the interval from a to b, which represents the area under the curve, equals capital F of b minus capital F of a, where capital F is an antiderivative of f. Now, since we already know how to find antiderivatives, calculating the definite integral becomes a relatively simple operation. By the way, this result is referred to as the second fundamental theorem of calculus. Let's revisit the problem of finding the area under the curve of f of x equals x squared over the interval from 0 to 4. This area is found with the definite integral from 0 to 4 of x squared dx. To calculate this integral, we first need to find an antiderivative of x squared. We find this to be capital F of x equals 1/3 x cubed. So by the fundamental theorem of calculus, the definite integral from 0 to 4 of x squared dx is equal to capital F of 4 minus capital F of 0, which is 1/3 times 4 cubed minus 1/3 times 0 cubed, which gives us 64 over 3, or 21.333. Note how this agrees with the answer we found previously. Let's look at an example. Imagine a computer's CPU utilization in percentages over time can be modeled by the function f of x equals 3x squared plus 4x plus 1, where x is in time in hours from the moment the computer is turned on. I want to find the total area under the curve, which represents the cumulative CPU utilization from x equals 1 to x equals 3 hours. Okay, to do this, we need to find the definite integral from 1 to 3 of 3x squared plus 4x plus 1 dx. An antiderivative of 3x squared plus 4x plus 1 is capital F of x, which is equal to x cubed plus 2x squared plus x. So the definite integral from 1 to 3 of 3x squared plus 4x plus 1 is equal to capital F of 3 minus capital F of 1. Well, this gives us 3 cubed plus 2 times 3 squared plus 3 minus the quantity 1 cubed plus 2 times 1 squared plus 1, which is equal to 48 minus 4, or 44. The cumulative CPU utilization is 44 percent hours. Okay, so this wraps up Module 11. What you should take away from this lesson is that we have found a tool which allows us to find areas of regions bounded by functions. Now there's a lot that goes into why this tool works, but using it is straightforward. And in the next module, we'll dive into more definite integrals and their applications.